Hello and welcome to the second episode of my tutorial about airline payload fuel optimization for a round trip between two cities. If you haven't watched the last tutorial, make sure you watch the first episode and then come back to this video so we are on the same page. Okay. What we have done so far is, if you have watched the last tutorial, we have used the MATLAB regression learner app, and we assume that we have a large amount of data available from our airline history, and we're going to create a model based on machine learning, based on regression methods, and specifically support vector machine is very good for this purpose. We're going to find some most important features, and then we're going to create a general model that can estimate the fuel burn for a specific flight for us without knowing anything else, without using any performance equation or Bergod equation or any other equation that we have learned in university. The most important features, as you have seen in the last video, is distance, block time, total weight, flight time, hour of day, fuel elevation in the destination and the origin, and day of the year, and payload. As I told you in the last tutorial, this is just an educational video, and we are not considering very specific constraint or a specific situation and operation limitation. So based on your project and based on your country, based on your airline and fleet, you might need some other features, or you might need some of these features. For example, fuel elevation might not be so important for you if your airline is operating on the flat space only, for example. So this is only an educational video, and just it's not just a real world scenario. It's just everything is just ideal. So make sure you just learn the concepts and change it based on your airline and your project. So we have selected our most important features, and we fit a regression learner for that. Now the next task is to define an optimization task. This part is not actually a machine learning or anything, if you want to say. It's just an optimization task. It's just a numerical optimization that MATLAB is very powerful at. So in order to optimize or create an optimization problem, we need to find our inputs, variables, and constraints. And also we need to have a cost function. So what are our inputs? What are our variables? So the origin and destination, of course, the off block and flight time, limitation, weights, very important, maximum takeoff weights. Some of the limitation weights are fixed, for example, or at least almost fixed, such as maximum landing weight, or maybe maximum passenger seat, maximum cargo seat, or some limitation like this. But some of them, such as maximum takeoff weight, is limited and it's variable during the year. For example, in my country, we have some airports below sea level, and we have some airports at 7,000 feet. And some days in the year we have temperatures above 50 degrees Celsius, and in the winter in some of the cities we witness minus 25 degrees or minus 20 degrees Celsius. So it's huge difference in weather, and it definitely led to maximum takeoff weights be changed during the year or even during the day. For example, in summer times, for example, an MD-82 may be limited to the temperature in some of the cities in Iran after 11 a.m. So most of the flights should happen before that, or at least in that city. So maximum takeoff weight can change a lot, and we should check for the performance charts and performance tables to update it in each flight. Other variables such as fuel, airport, and other prices. Again, this is one of the parts that you should change based on your needs and operation. The taxes, the ground service, the fixed prices or the dependent prices based on passengers, cargo, or maybe fuel. Fuel price might be different between two airports. So you should consider those. And the last thing is the ticket price. So what are our constraints? Again, the most obvious one are our limiting weights. So we shouldn't exceed the maximum takeoff weight, maximum landing weight, zero fuel weight, and so on. The maximum capacity, passenger, cargo, fuel tank capacity, of course, is obvious. And we need to have a specific reserved fuel when we get to destination. We cannot get to that destination with zero fuel. Because obviously our model is not perfect, so that's obvious. So again, this part is one of the specific parts that you need to change based on your situation. And what is our output? I selected the output for the simplest scenario available. We want to specify to the airline how many passengers or how many tickets you should sell in the first trip or first leg, and how many for the second flight or the return flight, and how much cargo you can bring with yourself, and how much fuel you should use in the first leg and how much fuel you should get on the second leg. That's our output. So it's generally one objective optimization, although it looks like we are optimizing many things, but we have included all of them inside our constraint function or in our cost function. So our cost function maximizes the total revenue. Revenue is, of course, income minus cost. There, at the end, our optimization would be something like this. For example, we are optimizing a flight between ICA airport of Tehran to Izmir airport, and we are assuming that the fuel price is much more cheaper in our home airport, in our base airport, and much more expensive at the destination. And there are other items that we can change and see the optimization. Okay, let's switch to MATLAB and see it in action. So it's because it's definitely might change between the values here and the values you get. Okay, in the last video, let's switch to this part. I've put the link for you for the GitHub repository and MATLAB file exchange, and again the links are available in the description here as well. You can download it from MathWork file exchange from this page, or even you can come to MATLAB and use the add-on explorer and search for it, and also you can use the GitHub repository if you like. Make sure you update it. Right now it's 1.2, but I'm gonna update it again today with the changes that we're gonna make right now, so it should definitely be something like 1.3 or more, or maybe 1.4. Go ahead and update it to make sure you are on the correct version. And if you have already watched the last video tutorial and downloaded the last package, it's the same, so you don't need to download it again because there's 2 folders here. In the first episode, we used our fuel estimator, and then now we are going to use round trip optimizer. Let's go to MATLAB. Just for a quick review, there is an airport that Excel files in the root directory that specify the airports your airline flies to. And there is a full data.map that is auto-generated when you use a fuel estimator. So make sure you have run the fuel estimator and have good amount of data before continue. Okay, let's switch to round trip optimizer. There are a few files here. The main file is the optimizer.mlx, which is a live script, and the get elevation, get distance, and cost function and constraint function are obvious. And the function that we're going to use inside is optimizer.mlx. Okay, there are some instructions here you can follow. Now I'm going to use SVM4 full.mat for the machine learning or support vector machine model. You can change it if you have a specific model. You can change it. This model is just a simple model that inputs the items that we saw in the last tutorial and output the fuel estimator. And one thing to mention: if you don't want this kind of detail, you don't want this much of details, you can skip these parts. You can just specify about, for example, you say I know that from ICA to Istanbul it burns about 8,000 kilogram of fuel. So I don't care if it is 8,000 or 8,300 or 7,800. I'm gonna specify that 8,000, and I'm gonna optimize other items. So you can skip these parts if you don't have enough data or you don't want this much of detail. Okay, let's continue. And if you don't have the full data, go ahead and comment this section, and then you have to disable this auto check mark as well if you don't have enough data. But assume that you have good data. Let's continue. First, we should specify our airport of destination and airport of origin. Let's start with a very simple, for example, domestic flight from Tehran to Kish Island, which is a domestic flight. Fuel price is the same at the both airports, and it's relatively easy example. If you check this auto, it will the code will automatically go ahead and fill the flight time, black time, I don't know, fuel elevation, distance, and all of them automatically from the database that we have on full data. But if you don't have full data, you must disable the auto and manually input these items for your specific route. Other items are pretty much self-explanatory, don't need any explanation. Off blocks, on blocks, and ticket price. Let's change it, for example, 1,000 tomans or 1 million tomans. Let's skip the cargo and make everything simple here. The cargo price would be 0. It means the cargo income. It means the incomes we get per kilogram of cargo in the leg, first leg and second leg. So let's skip those and don't make our problem much complicated. The most important item here is the fuel price. Fuel price in domestic flights in Iran is pretty cheap, so we put it on 1 in both sides. You might have some fixed cost per leg, cargo cost, I don't know, cost per passenger, such as catering, ground service, airport services. Cost per hour of operation is very important if you want to model those in your problem. For example, an MD-82 would maybe cost, I don't know, maybe it costs a few $1,000s per hour. So you can add them here. Maximum takeoff weight is very important, especially in summer times and when the airport's elevations are different. For example, we assume, just put a rough number here. Assume that maximum takeoff weight of the MD-82 is 70 tons in Tehran airport, which is field elevation is about 4,000 feet, and 72 tons at Kish Island, which is at sea level. Fuel threshold is the fuel reserve when we get to the airport. So the program automatically check if we get to the airport, no matter of the first airport or second airport. When we get to the airport, we should have at least 3,000 kilograms of fuel. And of course, not so much more than 3,000. Maximum landing weights of the first and second airports are almost the same for most of the airplanes. But sometimes it might change because of the airport elevations and these things, or maybe the PCNs of the airport. Maximum fuel tank, which is about 20 tons for MD-82, maximum zero fuel weight, empty weight, max passenger seats 160, and the max cargo, I put it on zeros to make sure we are not modeling the cargo. And that's it. Next step is to solve our initialization and definition. This part is mostly the programming part and the mathematical parts. Let's see the optimization task first here. As I told you, I'm not going to model everything in this specific example, so I use the optimization task GUI here, so you have a visual understanding of what is happening. But when you get along and understand what is happening, go ahead and copy this code and use the code only. Usually with the code you have better flexibility and you can change everything easily. But the GUI helps you to get started at the beginning. So I keep the GUI here so you can use it here. We have different options here. I've selected a nonlinear for our objective function, which is obviously nonlinear. Let's see our cost function here. This is our cost function. It inputs the up fuel. It means the fuels that we fill in the first airport, the fuel that we fill again or refuel, and the second airport, the passenger loads, which is pax load 1, pax load 2, cargo 1, and cargo 2. And it's gonna find the number of passengers. Our incomes would be this, for this simple scenario, our incomes would be the ticket income and cargo income. So cargo is 0, we forget about it, ticket income. It means the ticket price multiplied by passenger on the first leg and the second for the second leg. What are our costs here? Our cost is fuel cost, definitely. The amount of fuel that we refueled at the first airport and the amount of fuel that we took from second airport multiplied by the fuel price at each airport. Cargo cost, definitely cargo and ground services might cost something for us, so we're gonna ignore them here. The passenger cost, each passenger needs service, airport services, I don't know, catering and so on. At the end, cost would be some of these, and then revenue would be incomes minus costs. But remember, when you're using the solver-based method, solver-based optimization problems in MATLAB, it can always minimize, so it cannot maximize. So just put a -1 here. Minimizing the minus of the revenue means the maximizing the revenue. It's obvious. So this is our cost function. One more thing to mention, we are using a solver-based optimization task. The more modern version of the optimization task is the problem-based, which is much more understandable. It's more intuitive to just define your problem instead of defining your solver. It's very much intuitive, but it still has some problems or some compatibility problems, especially now that we are using constraint functions with the machine learning objects. So instead of making the problem much more complex, I decided to stick with the solver-based yet until the problem-based optimization tasks become much more easier to use for these advanced usages. Okay, now times for the constraints. Our constraints can be lower bounds for the zero fuel weights, maximum takeoff weights, and these things. But I just went to make it simple and created a nonlinear constraint. And we should specify the constraint functions from here. Both of them are from external functions. Let's open the constraint function solver. Again, we are using the train model and parameters here. Again, the inputs are the same with the cost function. We need to do some process such as finding the day of year, hour of day, and we're gonna create the input to our support vector machine or our model. Remember from the last episode, we took block time, flight time, day of year, distance, field elevation 1, field elevation 2, hour of day, payload, and total weight. So we create an input for our model. Then we are doing some weight calculation here, such as the payload is pax load plus cargo, the total weight is the up fuel 1, payload 1, and empty weight. We assume that in the origin we didn't have any fuel from the last flight, and even if we have, we are going to calculate it in up fuel 1. Then we are going to ask our AI model to tell how much fuel we're going to burn on this trip on the first leg. Then we're going to calculate those fuel and we find our fuel remaining, and then we have the fuel remaining and the weight at the destination. Now we're gonna do all the calculation again for the second trip or the return flight. We're gonna, but with one different. We should calculate what the fuel remained from the first leg as well. So the total weight would be up fuel 2, fuel remained from the first leg, payload 2, and empty weight. Again, we're gonna ask our AI model to predict the return trip fuel burn, and that's it. Then we're gonna calculate the landing weight at the destination and origin, the zero fuel weights at the destination and origin, and then we're gonna simply check for this 21 constraint here. Some of them are very intuitive or obvious. For example, we want the up fuel or the cargo or the payload or all the numbers to be positive. We cannot dump fuel, or we cannot have negative passengers numbers. Remember, the MATLAB and the solver has no logic. It only understands mathematics. So if you don't specify this constraint, it will say, okay, that's very good. We can have negative passengers. So our revenue is so much more. Okay, so you should specify all the constraints here. With the problem-based optimization task, this constraint would be much more easier to implement. The syntax of MATLAB for implementing the optimization task is that you assume that total weight minus the maximum takeoff weight should be less than 0. You should write it in this syntax. So whatever you put on this side should be negative. So if you want this item to be positive, you just put a negative here. If you want to make one of the constraints more aggressive, you can put a multiplier on that. That's so easy. These are the inequality constraints. If you have any specific equality constraints, that's the same. For example, imagine you need to have 100 passengers, exactly 100 passengers on the way to the destination. So you can say, okay, the pax load, pax 1 minus 100. You put it here, and that's you're good to go. Okay, these are the mathematical parts. Let's go for the results. For the solvers, you have different options here. fmin_con is usually the easiest one that can find the local minimum easily. Pattern search also finds some local minimum for you. And the best optimization for most of the situation is genetic algorithm. But genetic algorithm won't always give you the best solution. Let me make it clear for you with an example. Genetic algorithm needs time to develop. And when you start the genetic algorithm, you have no knowledge about your model. You know nothing about your system. You don't know what is maximum takeoff weight. You don't even know how you can get more income. So the system would take off with 0 fuel, or take off with 0 passengers, and say, okay, that's a good question, good problem scenario. So it takes time for it to develop, and it needs a very good model for your system. If you have a great model, a model that is trained with hundreds or thousands of data, and your model is pretty much distributed in all your space. For example, you have a model for if you have 10 passengers, and you have data of when you have 160 passengers. So your model can cover all your problem space. Then you can use genetic algorithm. If not, don't use genetic algorithm, because first of all, it is very time consuming, and second of it's most of the time it's not going to converge, or it converge to a non-feasible solution or not applicable solution. So what we're going to use a hack here, or maybe a trick here. We can use fmin_con and pattern search, but the problem with pattern search is that it is pretty much finding the local minimum. We don't want to find the local minimum, specifically now that our model is not very uniform. So what we're gonna do here, we're gonna use multiple start points here. I've created a multiple start point by myself, but I know the MATLAB has these options as well. So I've created a variable here, number of stars. You can increase it as much as you like. If you have time, you can put it at 100. It means it will find 100 random start points and will continue to optimize that from that start point. Because in pattern search and fmin cons, your solution and the quality of your solution is very much dependent on your starting point, from your initial point. So if you have an initial point that you know it's at least close to your optimum point, that's good. Even starting with one iteration is you will find the optimal point. But if you don't know exactly, go ahead and add this number, for example 10 or 20 or 5. And I have added a manual. You can add some manuals as well. For example, I put a manual item here as well, and then 10 random points here. So it's gonna optimize 10 times, and it will report all of the 10 iteration to me, so I can decide which one is better. Okay, let's start with our very simple simple scenario. Let's first start with fmin_con. Usually fmin_con won't give me the best solution unless I increase the number of stars to higher numbers, but fmin_con is much more faster. I usually disable the outputs, but here for demonstration I say okay, the objective values and feasibility, max constraint value, and maybe the current point. Let's show them and run it. If you're lucky, you're gonna see some blue items here. Blue items means it found some solution. It's gonna iterate for 10 times, and every time it finds the best function value. Remember, the negative items are good. We want to see the bigger negative items because we are minimizing the negative of the income. Okay, I'm gonna fast forward the video here for you. Okay, it's done. Very less than maybe 30 seconds. It's done. Let's come to the results. This is the final result. Okay, the best input that it found is we take 40 tons of fuel at Tehran and 800 kilos at Kish, and we take 136 passengers and return with 150 passengers. We get the revenue about 270 million. So, okay, I doubt this solution to be correct. This solution should go with much more time. So let's see how will it change with pattern search. Let's change the solver to pattern search, and everything is configured, so you don't need to change anything else. Let's run it again. Okay, it's done, and it took significantly more time, maybe about 2 minutes or 3 minutes. Let's see the results. I'm gonna close this and see the results here. Okay, I assume this one is the correct solution in the real world. And you can see we got 20 million more revenue. In the last one it was 280, and this one is 304. It says, okay, you can upfuel about 9 tons in Tehran, then you upfuel 6 tons at the destination, Kish, and in both lanes you have pretty much full passengers here. That's a reasonable. These other items are other local minimums that are being found. You can see this one is almost the same. It means all these two are converged to the same position in our problem space. These 4 items are converged to the same one. It gives you an idea of how you can manage your airlines as well. For example, this one is another local minimum. So imagine if you have about 150, you will have another local minimum. And these items are, it means you didn't take any profit. It means you had lost here. So these are the local minimums that are not, you shouldn't take care. Okay, let's make a scenario a little bit interesting. One of the most challenging routes for our project is from Tabriz Airport, which is in the northwest of Iran, to Istanbul. Let's put a few price would be something about maybe Sometimes the ticket price for the return flight is more expensive, so you can model that as well, and it will give you some interesting results. And the most important, let's don't change this item. The most important thing that should change is the fuel price. Fuel price at Istanbul is much higher than in Tabriz airport. So let's change this item to maybe 60 or even more. It's about 80. And let's see how much, maybe, no, let's 60 is better options. Let's run again with the pattern search. Another thing that I want to mention is that MATLAB has great functionality with power 4, which means the parallel 4. I couldn't make it work. I don't know why it doesn't work with global variables, and if I want to pass these variables to the constraint function or cost function, I should add it to arguments, and in that case I won't be able to use this GUI. So I had to stick with the normal 4, but if you are using the bare code, you can change it to power 4. And all this iteration will happen in much more faster, and most of them will happen in parallel. And as you can see right now, 1, 2, 3, almost 3 or maybe 4 of my cores are working right now. If you use it on parallel, all this iteration would be happening in parallel, and you will get much faster results. But this time it's not very important. If you know your route, you can select a specific route and a start point of 2 or 3, and it will give you the result in less than a minute or 30 seconds. And if you don't know and the route is new, you can start with maybe 100 starting point and let the program run. Let the program run for example 1 hour or 40 minutes or 30 minutes, and then come back, and then you have an overall view of the route and economics and managing your airline. So this time it's not so much when you compare the results and the knowledge it gives you from the route. And remember, we haven't modeled any of the real world scenarios, any of the constraints. Some constraints are political constraints, some constraints are limitation based on airport service, based on country, based on, I don't know, operation in that airport, based on weather. So if you add those to your route, you will get much more better results. Okay, kinda interesting results here. You see it is almost filled up, almost the tank are almost full, and we didn't took any fuel at the destination. That's interesting. We didn't take any fuel. So the interesting part is that we didn't say to our model, okay, the fuel price at Istanbul is expensive, don't refuel. The model decided to do that by its own. This is the power of machine learning and power of the mathematics here. And it decided to fill up and return with 160 passengers on the way back. So why it didn't took the full tank? The full tank is 20 tons. Why it didn't use the 100? It used 80 tons. That's because I think it's probably would be limited to the maximum landing weight. So it had to use less fuel in the way to Istanbul. Look at the second local maximum of the revenue. That's interesting as well. It took 160 passengers, okay, in the way to Istanbul, and it used less fuel. This is interesting. Although the fuel price is very, very cheap in Iran, it didn't fill the fuel. It didn't refuel to the maximum tank in Tehran, because it decided to refuel at Istanbul and always took more passengers. For example, in the high season that many people want to go to Istanbul, you can use this local maximum. That gives you an overall view of this. But let's imagine that the ticket price to Istanbul is maybe the return trip is 220. And for example, it's the beginning of the high season, and the prices to Istanbul is high, and the prices that come back from Istanbul is very cheap. And the fuel price is the same. Let's run the program again. It gave almost the same results, but with less revenue You see, it decided to took only about 600 kilogram of fuel at Istanbul because the passenger ticket is much more expensive in the way back. Look at the second item. The second item is the same. So you can see the point here. It tries, although the fuel price is very expensive in Istanbul, it tried to refuel again a little bit. And it also filled a little less at the airport of origin to make sure it will use all the seats available on the way back. You can see almost in all of the local maximums, we try to use all the seats available in the way back. This is the power of this optimization. And for the last check, let's put a very crazy value for fuel price. If you want to specify that, okay, for example, Istanbul airports won't sell us fuel. Say, okay, I'm not gonna give fuel to you, or I don't want to fuel because any reason. It could be political, it could be operational. So I don't want to refuel at that airport. So you put a crazy high value for the fuel price at the destination, and you'll add a pretty much big penalty function on that, and it won't refuel at Istanbul. Okay, let's take a look at the results. Results are very interesting here. Almost all of these numbers didn't give us any profit. As you can see, we are a loser here. Only one item gave us the best option here, which is actually not correct. You know why? Because it's kind of reasonable. You know, it says, okay, put 80 tons of fuel, bring 130 passengers to Istanbul, and almost don't return anyone from there. You know why? Because we specified that the ticket price of the return trip is too much lower than the ticket price of the trip to Istanbul. So that's exactly, I didn't expect this much of smartness in this code. That's very interesting for me. If you put the same price for the Tabriz to Istanbul and Istanbul to Tabriz, both of them cost about $5,000. Then this you would see something else there. For example, it would decide to take about 100 people to Istanbul and return maybe about 40 people, or maybe anything else. Just go ahead and play with this number. It will give you some great, interesting knowledge about airline operation. Just to wrap it up, let's see some other examples that I have played here. For example, the ICA with some more reasonable values in the summer times. Most of them are in summer. It's my birthday time, and it's July. And these are some more reasonable data here. For example, the ICA airport to Izmir airport, we decided to have 20 tons of, almost 20 tons, 90 tons, 20 tons of fuel at Tehran. Then we're gonna have 2 tons of fuel over there. It's almost, it says almost don't refuel at Izmir, or fuel only about 2 tons. These are some operation decisions for you. The payload will be about 111 passengers and return with 160 passengers. Again, why not taking 160 passengers to the way going to Istanbul? Because then you would be limited to the maximum landing weight. And keep in mind that the price for both legs of flight are the same. If we change the ticket price for one leg, again, this would give us some other interesting results. Another challenging route is from Mashhad to Najaf airport. Again, with the same situation, we decided to have 19 tons of fuel at Tehran, no refuel at Najaf. We take about 120 passengers to Najaf and 159 passengers back to Mashhad. Another operational decision here. Okay, let's wrap it up together. This is very simple word scenario, mostly educational, and to motivate you to use these tools, to use modern machine learning tools combined with optimization techniques and mathematics to predict and maximize your profit in an airline. It's not only airline. We decided airline because definitely I am going to be a pilot. I love aviation and these things. But if you're doing work in any other industry, you can use these tools. You can use machine learning to learn the patterns and model your industry, and then use the optimization tools to maximize or minimize something. These are some ideas that I have to continue in this project. You can use any of them to continue by yourself. You can model detailed cost per passenger, per hours, per legs, and detailed costs of your own country and your own operation. You can model operation limitation and constraints such as political or weather information. The more data you have, the better fuel estimator. In that case, if you have 100,000 of good data, then the fuel estimator for a specific registration of the airplane would be different from another registration. Even in some ideal and just dream model could even account for the pilot techniques. For example, a specific pilot with a specific registration would use less fuel than others because it tends to fuel more optimal. These are some dream works that can happen if you have a large amount of data, large amount of good data. A very good improvement that you can do in this project is to connect it to the weather API, such as Mathematics. Mathematics can not only predict the weather, it can use historical weather for any time and any point and any altitude that you want. For example, you can estimate, for example, right now the wind at Istanbul is, for example, 20 knots from, I don't know, 300 degrees. So it's gonna account for that. Or it will say, okay, at flight level 390 or at flight level 380 today, the wind is, for example, 80 knots from the east. So it will change your fuel estimator. It will improve your estimation, and then you can even select the time of the year. This is the next item that I told you. You can, in that case, you can optimize your off block and flight schedule. Then you can say, okay, the best time for this flight is at 8 a.m. because of many things, because of the weather, because of the wind. You're going to use one of the jet streams, you're going to use this tailwind on the way go, and again, you're going to use this tailwind, or you're going to avoid that headwind. So you can optimize for that as well. Another important and interesting solution or idea is optimize for ticket price. You can optimize for the ticket price and window price optimizing, so to tempt the passengers to buy your tickets, not your competitive. Based on your revenue, you can see, okay, if I do the flight at this time and I have this much of cargo and this much of passenger, then I have a very good revenue, so I can put some discounts on the ticket price, so more passenger would come to me and I will again get more revenue. These are the most crazy ideas you can use with these tools. Or you can compare different routes. Your model AI can understand the routes between the airports and decide which route is better in which season and which weather. So the sky is limit. You can add any more complex scenarios, any more constraints, limitation variable to your model and improve it for a real world scenario. Okay, that's it for this tutorial. I hope it will help you or help an industry and give you some idea to improve this by these modern tools that we have by MATLAB. You can also implement all of this with Python as well if you are a Python developer, but I mostly like MATLAB in these cases. Okay, if this video is useful for you, please leave it a like and subscribe to the channel if you don't want to miss the next tutorials about machine learning, aviation, and MATLAB stuffs. Until then, have a nice time and good day.